Just a minute. Okay, so in the previous lecture we discussed about how this buffer solution tries to maintain its pH value. Now there is one more term related to this concept, that is called Henderson-Hasselbatch equation. There is one more term related with this concept, that is called Henderson-Hasselbatch equation. We have actually considered that term. We were introduced to this term, that is pH is equal to pKa plus log of concentration of salt upon acid, or POH is equal to pKb plus log of concentration of salt upon base. How this equation can be derived, that we want to discuss. So Henderson-Hasselbatch equation is a kind of equation which is used to calculate pH of buffer solution. Henderson equation is a equation which is used to calculate pH of buffer solution. How that we can see. Now let us consider, in order to derive this Henderson equation, for this acidic buffer or for basic buffer, let us have an example of acidic buffer. Again, I recall you that this acidic buffer is a equimolar solution consisting of weak acid and is salt with strong base. Acidic buffer is a equimolar solution consisting of weak acid and its salt with strong base. Now in this buffer solution, in this acidic buffer solution, the dissociation of the acid can be expressed as dissociation of acid. So let us consider HA. Let us consider this HA is the weak acid. Okay, HA is the weak acid. So it will try to dissociate into H plus and A minus ions, and the dissociation constant K for this reaction can be written as concentration of product of concentrations of these two products divided by this concentration of the reactant, right? So the dissociation constant for this equilibrium can be written as Ka is equal to concentration of H plus ions and A minus ions divided by concentration of HA, undissociated HA. Or from this H plus ion concentration, will be Ka multiplied by concentration of HA divided by A minus. Okay, why we have taken this term? Because we want to derive a relation for pH of this buffer solution. And how the pH of the buffer solution can be calculated? We know this pH is equal to negative log to the base 10 of H plus ion concentration. So here, in order to understand this Hasselbatch equation, what we have considered? We consider an acidic buffer. Now that acidic buffer is having a weak electrolyte, that is weak acid. So if HA is the weak acid, it will try to dissociate into H plus and A minus. A minus is an in general anionic part. So that weak acid will dissociate into H plus and A minus ions, and therefore the dissociation constant for this acid will be given as H plus, concentration of H plus into concentration of A minus divided by concentration of HA. And therefore from this we can have this cross multiplication. So if we have this term, that is A upon B, that is equal to C upon D, if we have two equal fractions, then in that case we say that A multiplied by D, that is equal to B multiplied by C. So have that cross multiplication and get the value of H plus ion concentration. Again, why to take the value of H plus ion concentration? Because we want to derive the formula for pH is defined in terms of H plus ion concentration, right? So now apply negative log on both the sides, because we want to convert this term into pH. So apply negative log on both the sides. So if I apply the negative log on both the sides, negative log on both the sides, what will happen? This minus log of H plus will be, so this term, okay, this term will get converted into this term. It will get converted into this term, right? So H plus ion concentration would be Ka, where K is the dissociation constant of the weak acid multiplied by concentration of acid divided by concentration of salt. Concentration of acid divided by concentration of salt. So if I apply negative log on both the sides, what will happen? What will happen? So here minus log of H plus, that will be equal to, here this is a product term, right? This is a product term. We want to keep this fraction as such in the log term, okay? And here this is a kind of logarithm of m into n. So logarithm of m into n is log m plus log n, right? Log m plus log n. So here this minus log of H plus is equal to minus log of Ka minus, actually it would be, it can be written in this way. Let us write. Okay, this can be written as minus log of H plus ion concentration, applying log on both the sides, minus log on both the sides. Okay, so here log of negative log we are putting here, okay, plus minus log of concentration of acid upon concentration of salt. Okay, so we can write this term, right? And this is nothing but this term. So negative log of H plus ion concentration is equal to negative log of Ka minus log of concentration of acid upon salt. But see the definition of this minus log H plus, that is nothing but pH. So this term is pH, this term is pKa. Now here minus sign is there. If I want to remove that minus sign and bring here plus sign, I will have to reverse this ratio. I will have to reverse this fraction. So I need to take the salt in the numerator side and acid in the denominator side. So what we have seen here, we have seen up till now we have considered here an example of acidic buffer. That acidic buffer solution will consist of H plus ions and A minus ions. Those are obtained by the dissociation of this weak acid. So if we apply the law of mass action to this dissociation equilibrium, we get that dissociation constant K is equal to concentration of H plus and concentration of A minus divided by concentration of undissociated HA. So where if we want to calculate pH, we should be able to know what is the H plus ion concentration in this solution, and therefore we write this expression, convert this expression in the form of H plus ions, and then we apply negative log on both the sides. So applying negative log on both the sides, we come to know that by definitions, this negative log of H plus ion is the pH of the solution. Negative log of log Ka is nothing but pKa, and this is the term. And if I want to reverse this term, if I want to bring here plus sign, I need to write here salt concentration in the numerator side and the concentration of weak acid in the denominator side. And therefore what we will get, if we put these two values in this equation, what is this? This is pH, this is pKa, right? Minus log of acid upon salt. Okay, is it fine? So minus log of H plus, that is pH, right? That is equal to, I will write it. Okay, so this term is nothing but pH. That is equal to, this term is nothing but pKa. This is nothing but pKa minus log of concentration of acid upon concentration of salt. Now we are we are very close, we are very close to the Henderson equation, that is pH is equal to pKa plus log of concentration of salt upon acid. Okay, so just if I want to convert that, if I want to convert that, that can be written as pKa. Okay, so I need to reverse this sign. I need to reverse this sign, and I can write here concentration of salt upon concentration of acid, upon concentration of acid, right? So pH is equal to pKa plus log of concentration of salt upon concentration of acid, which is nothing but the very famous Henderson equation, or that that is also called Henderson Hasselbatch equation. That is called Henderson Hasselbatch equation. And therefore what we can write, pH is equal to this term, or if I want to remove this minus side, I need to take its inverse. I need to take the inverse of this fraction. Okay, so it will be pH is equal to pKa plus log of concentration of salt upon concentration of acid, and this is called the Henderson Hasselbatch equation. This is called the Henderson Hasselbatch equation for acidic buffer, for acidic buffer. Now we can derive a similar formula for calculating the concentration of OH minus ions, or calculating the POH of the basic buffer by using such kind of analogous calculations, right? So this is Henderson Hasselbatch equation. What is Henderson Hasselbatch equation? Very first thing is it is used to calculate something. What is that? pH of buffer solution. pH of buffer solution. How the Henderson equation can be derived? Let us consider an example where, let us consider the example of HA, which is the weak acid in this acidic buffer. So that acidic buffer is dissociating. It is dissociating into H plus and A minus ions. And if we apply the law of mass action to this dissociation equilibrium, we can find out the concentration of H plus ions. We can find the concentration of H plus ions from this dissociation, and therefore if we want to get the pH of this buffer solution, we need to do some mathematical manipulation, we need to do some mathematical calculation. So that is apply negative log on both the sides. So if we apply negative log on both the sides, we, and if we look at here, this pH is this term, pKa is this term, so it will be this in the next step, and in the last step we will take the inverse of this to remove this minus sign, so that we get this Henderson Hasselbatch equation. So this was the derivation of Henderson Hasselbatch equation for calculating the pH of an acidic buffer. In a similar way, we can calculate pOH of basic buffer by using an analogous example. Okay, by using an analogous example. Now what is at this last point, we will see what is the significance of Henderson equation, or what are the applications of Henderson equation, why it is so important, See, the first thing, if we look, the first application of this Henderson equation is to calculate pH or pOH of buffer solution. This Henderson equation is used to calculate pH or pOH of buffer solution. The second thing is, if the pH of solution is known or pOH of the solution is known, then we can calculate the dissociation constant of that weak acid or weak base simply from the pH or pOH values. How? Okay, by using this relation. So if we know the pH or pOH value, we know ultimately what is the concentration of salt and what is the concentration of acid, because the buffer is prepared by a particular chemist, by a particular researcher. So he knows how much salt is added, how much acid is added. Okay, so if we know the pH or pOH, that can be practically determined with the help of pH meter. So if we know the pH or pOH solution, we can calculate this Henderson equation to calculate the dissociation constant of weak acid or weak base. And this solution also helps to prepare a buffer of any desired pH. It helps to prepare a buffer solution of any desired pH by adjusting this ratio, that is the salt of concentration of acid and base, or concentration of salt and concentration of weak acid. Okay, so these three applications can be remembered, can be understood if we look at this equation. The first thing, to calculate pH or pOH. Second thing, to prepare a desired a solution, a buffer solution of desired pH or pOH. And third, to determine the pKa or pKb of the buffer solution. Okay, so pH of the buffer solution can be calculated with Henderson equation. pKa or pKb, that is Ka or Kb, which is nothing but dissociation constant of that weak acid or weak base, can be calculated if we know the pH value or pOH value of that buffer solution, which can be calculated practically, which can be determined practically with the help of simple pH meter experiment. And the third application is that we can prepare a buffer solution of a desired pH. If we can prepare a buffer solution